Hi, this is Mathman here. Typically, I like to keep my introductions short so that we can get right into the subject. But I just want to make note that we're holed away in our home because of the coronavirus scare. I'm a high risk individual, both from a health point of view and age. And so we are isolating ourselves from the rest of the world until this thing shapes up a little bit further. I have family members that are experts in the area of infectious disease. And when they're concerned, then I'm concerned. And they were intimately involved in research and development for a major pharmaceutical company in infectious disease, so they know what they're talking about. So, following the CDC instructions and doing the best I can. Now, on to the math. My ultimate goal is for us to move into calculus, and hopefully I won't come down with anything before then, prevent me from making any more videos. My grandson had come down with 104 fever, and now they're staying away from us, isolating from us. Hopefully it isn't coronavirus that he has, but who knows what it is. We just hope that he gets better soon. Poor little guy. And now my daughter is suffering from this same thing, and we've had pretty close exposure to them, so we're monitoring ourselves on a day-by-day basis. My wife thinks that she may have a sore throat, so we're waiting. But anyway, I watched a couple of bald eagles fishing. Nature goes on, and so will we. Typically, math courses leading to calculus touch on all of the subjects that we have covered. Some of them are more important than others, but there are two topics that we haven't covered yet that are typically covered in a course, either in a calculus course or in a course before calculus, and that they're integral in understanding calculus. Now, what mathematicians don't tell you, and what I think they do this on purpose. The idea of Newton suddenly having this flash of insight and having the mathematics all straightened out in his head as it's printed out in a book with all of the nomenclature and terms. This is a typical calculus book. This is one that is a classic or has been a classic for many, many years in colleges. This was from Yale or Harvard, Yale, I think, yes. The Thomas Calculus and Analytic Geometry. Yeah, there's some good things in here, but it's not necessarily an easy book to understand. You have to really understand the language of mathematics, and it doesn't give you the chance. You're struggling with the language and nomenclature, and you don't really get a firm feel or understanding of the concepts behind it. Remember, Newton, when he thought of calculus, didn't come up with the whole thing where he's talking about epsilons and infinitesimals where they um, are not quite zero, but they're in essence zeros, and that there was a criticism of the basis, the philosophical basis for calculus, and they called infinitesimals ghosts of numbers departed, and something of the without real substance, but are meaningful nonetheless. And so there was a real problem with mathematics that the mathematicians will not tell you about in a class. That calculus did not have a sound theoretical basis until the mid 1860s, where Bernhard Riemann developed his approach using limits. That's a topic that we'll be talking about, and the fundamental theorem of calculus. But he proved calculus from a different conceptual point of view than Newton, who was thinking in terms of infinitesimals, and he called them fluxions. And it wasn't until 1967, I was 12 years old in 1967, when a mathematician had proven from Newton's perspective the philosophical foundation was sound for calculus. So here mathematicians are teaching a topic to students, and I think they deliberately intimidate students, and they don't let. I think it would be helpful for students who are struggling with concepts, because math is not an easy subject. There are a lot of conceptual ideas in mathematics that just are difficult for us to grasp, and and it would be helpful to students to understand that it's natural, that this is not an unnatural thing, that even the mathematicians themselves, and they don't want to admit this, didn't have a sound foundation for calculus for nearly 200 years before Riemann came along and proved it to be sound using the fundamental theorem of calculus. But then it was another 100 years from Riemann to prove calculus on a philosophical basis from Newton's perspective and from Leibniz perspective, Gottfried Leibniz. I don't want to even go into the feud between Newton and Leibniz. You read that on yourself. It's a very interesting historical note. But Newton, I think Newton really did have a valid argument there. And regardless, Newton was a mathematical genius, even if he was a little on the quirky side. Smart people can be dumb. For example, he wrote copiously on the book of Daniel, on the prophecies in the book of Daniel. He was a religious fanatic. He also was very much given to alchemy, which had no scientific basis whatsoever. And yet here's a father of the scientific method and of the mathematics that became the foundation for science, the language of science, interested in essentially pseudoscience. So smart people can get themselves involved in silly things that are contrary. That's part of the dichotomy of human nature. So what we're going to discuss, and I've gone 10 minutes on this from a philosophical point of view. I just want you to understand that if you're having a hard time understanding some of these things, it's natural, and don't feel intimidated. Just work at it, and maybe things will start to be clear. Don't give up. It's easy to give up. So let's talk now about two topics. One of them is called series and sequences, and the other is limits. And I don't think we're going to get through all of it in this one video, but at least we'll get a start. Okay, so let's go to our whiteboard, and we'll get started on sequence, and I'll try to keep it as plain as possible. Again, I'm going to give a plug for this book. I think if there ever was a self-help book that was excellent for preparation for understanding calculus, it is this one. And I'm going to give a plug for another book that I had, 5 Equations That Changed the World. And one of them is Einstein's special theory of relativity and general theory of relativity. This one, that chapter. There's a story here about Daniel Bernoulli, the son of, I think it was Johann Bernoulli. Bernoulli's principle, Daniel Bernoulli, fluid dynamics. And fluid dynamics is the mathematics behind airplanes, why they fly. Between a rock and a hard place, 65. And also, what this book does is it gives you a little vignette on the personalities involved in the mathematics, besides the mathematics, between a rock and a hard life. Daniel Bernoulli was the son of Johann Bernoulli, and Johann was an absolute asshole, okay? Let's just put it that way. One of the great fathers of calculus and mathematics, modern mathematics, was a complete and total asshole. And he stole his own son's equation and published it and claimed it to be his own and tried to ruin his own son. But if it wasn't for Leonard Euler, who happened to be a good friend of Daniel Bernoulli, who stood by his friend Daniel against his father, Daniel finally gained the credit for one of the greatest equations, mathematical equations, that revolutionized humankind. So it not only talks about water distribution and how fluids move, air moves, weather, but also aircraft. That's one of the key principles behind lift on a wing, is Bernoulli's principle. So I recommend this book. I think it's easy reading for most people, at least the bio part of it is. The mathematics is usually pretty simplistic and enough to understand. You'll get a very good idea of how Einstein derived his famous E equals mc squared. So maybe we can take a look at that at some point. There's just an infinite number of topics in mathematics. And another, I guess I'm giving book plugs right now. Here is Theoni Pappas, Joy of Mathematics. It is multi-topical, as many topics as you can. There are vignettes. There's nothing, no topic is discussed in anything more than 5 pages. As a reference, she's just phenomenal. Here she talks about Pythagorean Theorem, and how you can come up with the exact square roots without having to actually calculate them on a number line. You do it prime numbers, and series and sequences are very involved in that. And I mentioned Riemann, and if you ever saw the movie An Incredible Mind, and when he's coming out of his delusional states and getting off the medications, you'll see him in the Princeton Library, the mathematician, what was his name? John. Oh, that's terrible to get old. Anyway, he was writing on a window inside the library, the Princeton Library, and a mathematics student comes up to him and recognizes him and says, "Oh, you're working on Riemann." And he says, "Yes." They didn't explain Riemann at all. But that's one of the millennial problems. Now, if you solve that, you get all kinds of fame and fortune. The Riemann hypothesis is related to a sequence, and we'll be looking at series and sequences in this next section. But it deals with how series and sequences deal with in the complex domain. When we say complex domain, that is how including real numbers and imaginary numbers, and the behavior of the function over that domain, and where that function is zero. And the hypothesis is that the real part must be 1/2 for the zeta function, what they call the zeta function, to be zero, what they call non-trivial zeros, or trivial zeros and non-trivial zeros. So anyway, it's all lingo, but whenever the function is zero, the real part of the zeta function is 1/2. So it sounds simple, and many of these problems are, like Fermat's famous equation, which is related to the Pythagorean theorem. The Pythagorean theorem, remember, we got a right triangle, and we have the x portion, we have the y, and the Pythagorean theorem says this is that the hypotenuse is x squared plus y squared, and that's the Pythagorean theorem. Well, it can be written like this. And what Fermat said, well, for any n, let's you know what? Let's make this another number. Let's make this r, and let's make that r, so that we're not confusing things. Fermat's theorem said that there was no solution to this equation for n greater than 2, greater than and equal to 2. Oh, not equal to, because it's greater than 2. For any integer, n, integer. And you know what? That was proposed in the 1600s by Fermat. And it was in the note. What was so perplexing about this was that in the column on the margin of a book that he was writing in, I think it was his diary, in the column of his diaries, Fermat writes, I have an elegant proof, but this margin is too small to contain, too small to write it down or contain it. And that tantalized mathematicians for hundreds of years until around 1922. 1992, there was a mathematician in Princeton who worked it out, and it apparently was very, 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 very complicated proof. And it took years for people to verify that the proof was valid. But when they did, he got credit for solving the oldest and most perplexing problem, Fermat's last theorem. And there are a series of other problems that are called the millennial problems. And the Riemann hypothesis is one of them. And the Riemann hypothesis deals with a series and sequences. So, what is a sequence? Well, a sequence is just an orderly arrangement of numbers according to some pattern. Okay, all real integers is a sequence. So let's say if we have n, then I of n is the sequence. So let's say n is 1, 2, 3, 4, 5, 6, 7. These are the different terms going on forever. The integers are 1, 2, 3, 4, 5, 6, 7. And what you can say is that the next integer in the series is equal to the last integer in the series plus 1. So if n equals, let's say, 5, then I, 5 plus 1, is equal to I, 6, which is equal to I, 5 plus 1, and that's equal to 5 plus 1, or equal to 6. Now, this is really a trivial example, but this is one everybody knows and deals with because it's a set of all integers, real integers. And that little formula tells you how each integer in the sequence is written. So you got I n plus 1 equals I n plus 1. All right, so that's the algebraic form that describes the sequence of integers. And so integers are written, a sequence is written as an orderly arrangement of numbers. So let's say we have I, n, the sequence, we have n, and we have the first term, second term, third term, fourth term, fifth term, sixth term, seventh, eighth, 9. It goes on forever. And we're just going to write that. We're going to say the corresponding integers for, and they're written with commas between because it's just an order ordered arrangement of numbers. Another one would be n equals 1, 2, 3, 4, 5, 6, 7, and forever. And our sequence is 2, 4, 6, 8, 10, 12, 14, on and on. Well, this can be written in algebraic form that each advancing term of this pattern of integers is equal to the last integer of the term of the sequence plus 2. So if we want to know what I7 is, we see that I7 is I6 plus 1, and that's equal to I6 plus 2. Well, what's I6? I6, well, this is n equals 6, and I6 is 12. I forgot my commas. This is important as sequence to separate each term with a comma. I6 is 12 plus 2, and that's equal to 14. So this is I7, and we can see that there. And you can have an infinite number of these different sequences. One of the most famous sequences is one that is a particular favorite of mine, is the Fibonacci sequence. And the reason for that is that Fibonacci numbers are found everywhere. So this is the Fibonacci sequence. And Fibonacci was a 12th and 13th century Italian mathematician. He wrote a book called Liber Bacci. I think I butchered the name. It means about calculating in Latin. And in this book, he advocates the use of Arabic notation, which is base 10. We talked about bases. And we are represented by these numerals. This is called Arabic numeration forever. Before Arabic numeration, he introduced this in his book Liber Bacci, which was 1200 or 1202 AD. And Fibonacci, or his name was Pisa, or let's say Leonardo of Pisa, or Fibonacci, the son of Bonacci. And he advocated the use of Arabic numerals because his father was a merchant, and he noticed that the Arabs that he traded with in northern Africa were able to do quick and easy and accurate calculations using these numbers. Whereas up until that time, Western Europeans were still using Roman numeration, which you can't. What is 4 times 50? You can't use this. This is no different than writing words. So Roman numeration stymied mathematics and the progression of mathematics in Europe for hundreds and hundreds of years until Leonardo of Pisa introduced Arabic numeration in his book Liber Abaci. And in this book, he gave a little problem with an algorithm in it. They didn't call them algorithms then, but it was a set of instructions. And you start out with a pair of rabbits, and at time 0 in the first month, you skip a month, they have no offspring, and then from every month thereafter, they give rise to a set or a pair of offspring. So this is our original pair. And they have another pair in the 4th month. And these guys, they skip a month, but then they have some. So this original pair, they have another pair, and then this pair, they skip a month, and this pair has a pair, and so on. And the question was, after 12 months, how many pairs? And you see, without Roman numeration, where you got 1 and 1 and 2 and 3 and 5 and 8 and so on, you couldn't calculate these things very easily. It took Roman numeration to be, or Arabic numeration, for you to be able to figure out the number of rabbits. And it turns out that this sequence, which has become very, very famous in the last, since 1963, really, or actually since the 19th century, when the French mathematician Edouard Lucas studied series and sequences, and in particular, the sequence in Liber Abaci. He named that sequence the Fibonacci sequence, and there's a correlating sequence called the Lukas sequence. Lukas is the guy that came up with what they call the Tower of Hanoi, the little discs that fit on a peg, and you got 3 pegs, and you got to move all of them to another peg without having a larger disk on a smaller disk. And it's a little game you used to see a lot in, highway cafes and stuff. keep your mind occupied, play with while you were waiting for your dinner. And I don't know if I haven't seen the Tower of Hanoi in a toy store in a long time. I wonder if they still sell it. But that little game, that was devised by Edward Lucas, who named the Fibonacci series the Fibonacci series. And it goes like this. We have n terms, term 1, term 2, term 3, term 4, 5, term 6, term 7, term 8, and we'll go on forever. And the Fibonacci sequence is 1, 1, 2, 3, 5, 8, 13, 21, on. It goes on indefinitely. And the Fibonacci sequence, algebraically, each subsequent term, the last term, is found by the previous term plus the term before that. So, in other words, this term, the last term in the sequence, let's say this is f, let's say n is equal to 5, okay? So f6 is equal to f5 plus f4. So what's f5? Well, here's n equals 5, and that's 5 plus, and f4 is 3. So 3 is 8, and you can see right there. So these being a sequence, we've got to put commas there and so on. And this is a very, very famous sequence that goes on and on and on, and it's very strongly connected to something that we'll look at called the golden ratio. But this is a very famous sequence. So the algebraic formula for it is f sub n plus 1 equals f sub n plus f n minus 1. I mentioned the Lukas sequence, L sub n, 1, 2, 3, 4, 5, 6, 7, 8, and Lukas sequence is starting with 1 and 3 instead of 1 and 1. And 1 and 3 is 4, 3 and 4 is 7. It's the same thing. Ln plus 1 equals L sub n plus Ln minus 1. And so these are the different terms in the Lukas sequence. That's 29. 1, 2, 3, 4, 5, 6, 7, 8. That's 37, 47, and on. This one progresses a little faster. And that's the Lukas sequence, named in the honor of the French mathematician Edward Lucas, who lived in the circa the late 19th century, circa 1890s, maybe earlier, mid to late 19th century. I don't know when he died. Another sequence is we'll call it S, and that's equal to 1 on 1 squared. And we got 1 on 2 squared, 1 on 3 squared, 1 on 4 squared, 1 on 5 squared. So this is equal to n. Let's just make it a table. We got 1, 2, 3, 4, 5, 6, 7, 8. And this is 1 on n squared. But that's 1 squared. This is 1 on 2 squared. This is 1 on 3 squared. This is 1 on 4 squared. And 1 on 5 squared. 1 on 6 squared. And so on. 1 on 7 squared. Now, this one, when we look at series, becomes important. You can have all kinds of sequences. And one of the interesting things about the Fibonacci sequence, and we haven't looked at it yet, is if we look at the Fibonacci sequence, we go n and f sub n. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, on forever. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144. All these separated by commas. And we know that the formula Fn plus 1 equals F sub n plus F sub n minus 1. That's our mathematical formula for Fibonacci numbers. And if we take the ratio of Fn plus 1 to F sub n, let's take a look at that, okay? So we're going to look at the ratio of Fn plus 1 divided by F sub n. And so we've got n, we got Fn and Fn plus 1. All right, and then we're going to have this ratio Fn plus 1 on Fn. So we're going to make this table, and this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It goes on forever. Fn is 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. And this one is 1, 2, 3, 5. It's just one term ahead. 8, 13, 21, 34, 55, and 89, blah, 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 blah. Those 3 dots mean it goes on indefinitely. Okay, that's really what that means. Now, the ratio here is 1 on 1, 2 on 1, 3 on 2, 5 on 3, 8 on 5, 13 on 8, and down here we got 89 on 55. All right, so this is 1, this is equal to 1.5, 2, sorry, 2. This is 1.5, this is equal to, oh geez, I got my calculator here. Sometimes it's quicker than doing stuff in my head. All right, come on now, find the calculator. All right, 5 divided by 3 is 1.6. Wow, 1.666, blah, blah, blah. And 8 divided by 5, 8 divided by 5 equals 1.6. And 13 divided by 8 is 1.625, and down here where we have 89 divided by 55, we got 1.618, 182, and if we kept going, this would be 233 on 144. 233 divided by 144. Again, it's 1.618 and 1. And what we find is that when you got this ratio like that, we approach a number. So we got fn plus 1 on fn, and as n gets big, this ratio n plus 1 on fn converges. This ratio converges to this number, the square root of 5 plus 1 on 2, exactly. And we call this phi, and phi is the golden number. We're going to be looking at the significance of Fibonacci numbers and the golden number. I'm just whetting your appetite. But the golden number is found all over the place, as are Fibonacci numbers. And we can see that, let's say, the set of integers is 1, 2, 3, 4, 5, 6, 7, 8, forever. And the set of Fibonacci numbers are 1, 1, 2, 3, 5, 8, 13, 21, forever. Now, there are big gaps. Each number here is a Fibonacci number, but 4 is not. 7 is not a Fibonacci number. 12 is not a Fibonacci number. In fact, a lot more numbers, as this sequence grows, you can see that the gaps between numbers increases. Here the gap is 8, but this gap is 13. This gap is 21. And so there are 21 numbers in between 34 and 55 that are not Fibonacci numbers. Yet, this sequence is indefinite. It's interminable. It just goes on forever. So what does that mean? That means that the set of numbers that are Fibonacci numbers is infinite. But so is the set of integers. It's an infinite set. And it has more numbers in it than the Fibonacci numbers. And this is what's interesting, that not all infinities are the same. So you may run into this a little later, but there are inequities between infinities, and this is one place where you find it. Infinity is not the same for everything. So those are sequences. Now a series, on the other hand, is related to a sequence in that it could be an ordered arrangement of numbers, but these are numbers that are added together. So remember our sequence our sequence where we had, we called it S, and we had 1 on 1 squared, 1 on 2 squared, 1 on 3 squared, 1 on 4 squared, 1 on 5 squared, 1 on 6 squared. These are the individual elements of a sequence S. But if we want a series, we'll call it S prime. A series would be if we added these. Added each term. That would be a series. So this is a sequence where each of these is an individual element, and a series would be if we added those elements that make up the sequence. And in fact, this is a very important sequence, or series, I'm sorry. This is an important series. It was studied by Euler, and it's found to go to a certain number. It equals 1.6. No, wait a minute. I think it's 6 something. Let's see. Let's look at this. S prime equals 1 plus 0.25 plus this is 1/9, whatever 1/9 is. 1/9. And that's 1, 1, 1 plus 0.111 plus 1/16. 1/16. This is 0, okay, 5, 6, 6, that's 36, 96, 40, okay, 3, 2, that's 2, 32, this is 8, all right, 5, so that's 0.0625, and if we just kept adding these terms together, each term gets smaller, plus 1 on 25, plus 1 on 36. You can see each term is smaller and smaller, and eventually it converges to a certain number, and I can't remember exactly what that number is. I'm just going to take a look real quick. I should have had this written down. I'm sorry. Riemann Hypothesis. Yes, this is related to the Riemann Hypothesis. And Riemann was Riemann Zeta Function. This is called the Zeta Function. And Leonhard Euler looked at this particular problem. For this situation, it was squares. And he found that this was, oh, guess what? I gotta look at the function. I think it's, damn, I can't remember. It's 6.3 something, I think. If we just continue adding those numbers, there's a way of figuring it out. But what you do is you'll see that this number will will progress like this, and that there will be some limit beyond which S prime is less than the limit, and it converges on a certain specific number. And that, so we say that this series converges. If the series just kept growing, for example, it's obvious if this were the other way around, if this S prime was equal to 1 squared plus 2 squared plus squared plus 4 squared plus 5 squared plus 6 squared, it goes on, then we'd have 1 plus 4 plus 9 plus 16 plus 25 plus 36. And each term that we add, this thing would get larger. And so it would become very large. Let's say if we had 100 squared, and we're adding it, and it gets very big very quickly. So this is said to diverge because it's not closing in on a particular number. So some series converge and some series don't converge, and that's been a problem for mathematicians for many years, to prove that certain functions, and these are called functions, converging. This particular function, specific values, let's see. Okay, here it goes. This, yes. This one we call the zeta function is equal to the sum, and this is the notation that's given. N equals 1 to infinity because it never stops, 1 on n squared. So that is equal to, when n is 1 squared, plus, because the sum means each term is added, so that's what that sigma means, that each term is added. Next term is 2, n equals 1, 2, 3, 4, 5 to infinity, so we got plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus, and it goes on indefinitely. But this, because of the nature of this actually converges to a specific number, pi squared over 6. And how do you prove it? Well, you can add forever, and you can see that, like I said, if you plot it, you'll see that this will, and here's 2, it will asymptotically approach 2, or actually it approaches 1.64, I think, 493, so on. This is an exact number, though. And you know that pi is an irrational number. It's 3.141592365, I think, and so on. It goes on forever. It's non-repeating, never-ending decimals. Some people have pi memorized to 1,000,000 places. I don't know how the hell they do it. But pi is a special number. The Greeks called it irrational. It's just basically the circumference and the radius, where the area equals pi r squared, and the circumference equals 2 pi r. And so when you have the area divided by the circumference, you have pi r squared on 2 pi r, cancels out. So we have twice the area over the circumference equals the radius. Or whoops, yeah, that's correct. But also, let's see. Okay, it's 2 pi r. So pi is equal to c on, okay, the ratio of c on the diameter. Okay, so that's pi is the ratio of the circumference to the diameter of a circle. That's where you get this number, and it was of great interest to the ancient Greeks. They called it irrational because they certainly didn't like it. And there were a lot of irrational numbers like the square root of 2 and others. Pi was a specific irrational number. So this is called the Zeta function. And if we have a series, zeta is equal to the infinite sum of n equals 1 to infinity of 1 over n to the x. And x can be any number. In fact, over the entire what they call range of complex numbers, of all numbers, complex numbers and real numbers. So x could be so we have 1 over 1x plus 1 over 2x plus 1 over 3x. We saw in the case of x equals 2 that this goes to pi squared on 6. And when you take this series over the entire range of numbers, complex and real, n equals 1 plus blah, blah, blah. This is called the zeta function, zeta of x. And it has, if you plot this thing over its entire domain, it actually gives you a really wild pattern. Here's one photograph of that. Hopefully I have it positioned right. That was colorized to make it stand out. But the Riemann hypothesis, this is it here. This is, again, the zeta function plotted over its domain. And you can see, it's a little difficult to see on this, but you have a 0 there. You can see that the function crosses the 0. Both the red is the real portion of x, and the blue is the imaginary portion or complex portion of x. And plotted separately, they both cross the 0 line numerous times, in fact, an infinite number of times. And it does so when the real part is 1/2. And that it sounds somewhat simple, but nobody's been able to prove it. When it says it has zeros only at negative integers, negative even integers, and complex numbers with real part 1/2. And so it sounds like a fairly straightforward problem, but people haven't proven that to be true in a long, long time. And what's interesting about this zeta function is it has something to do with how prime numbers distribute. And you know what a prime number is. Let's say we have our integers, okay? So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, it goes on forever, okay? Now, a prime number is a number that's only divisible by itself and 1. So here we have 1 divided by 1, so that's prime. 2 divided by 1 and 2 divided by 2, so 2 is prime. 3, it has no factors. It's only divisible by itself and 1, so 3 is prime. 4, however, it's not divisible by 3, it's divisible by 2. 4 is 2 times 2, so it has factors. It's not prime. 5 is prime. 6 is divisible by 3 and 2, so it's not prime. 7 is prime because it's only divisible by itself and 1. But 8 is divisible by 4 and 2, and so it's not prime. 9 is not prime. It's divisible by 3, so it's not prime. 10 is divisible by 5 and 2, and it's not prime. But 11 is only divisible by itself and 1, so it's prime. And 12 is not prime, and you get the idea. And if you look at these numbers over, let's say, from 1 to 1,000, or 1 to 100,000, you could see that the spacing between prime numbers increases. And so the Riemann hypothesis is connected to how what they call the distribution of prime numbers in the set of real numbers. How do they distribute? And it's interesting. I did this. I wrote a program the other night that calculated prime numbers up to. I found. I ran into a problem. I had a variable overflow at 60,000 terms. So, but when I looked at the function, and here I have a problem here. This darn timer goes to default screen. There we go. Now, if I can just open up that program that I called prime. Just 1 second, bear with me. Here it is, prime. Now, I plotted, oh darn, guess what? I think I lost it. Anyway, it turned out that if you plot it on a log-log scale, so when both axes are logs, so the first is 1, second is 10, third is 100. The fourth is 1,000. Fifth is 10,000. You're going up an order of magnitude each time. And the same with the y-axis, 10, 100, 1,000, and 10,000. The prime numbers plot a perfect line through a log-log scale. So these are prime numbers, the way they distribute. The way they distribute among the real numbers. So this is the real numbers, and this is prime numbers. Whoops, I meant right. And this is the way they distribute. And they're intimately related to logarithms, and the zeta function makes a statement of how these prime numbers distribute among real number, the whole set of real numbers. Now, that's why anybody who solves the Riemann problem, unlike the Fermat's last theorem, that was just a curio. That was not a meaningful problem, really. It didn't make much of a difference to the world of mathematics. The Riemann hypothesis, on the other hand, is deeply and intimately related to many applications in physics, and people would love to see that problem solved. But anyway, I've kind of explained it to the best of my ability, and it all comes out of series and sequences. So we looked at what a sequence was, and we looked at a series. Here's one more interesting thing. A couple more points before we quit on this subject, and I think the next video we'll talk about limits. We mentioned convergence, we mentioned divergence among series. Okay, so we're going to take a look at what was that I had in mind? We're going to take a look at a series. Okay, so let's say we got a series S. Whoops, I'm sorry, S. And S is an infinite series, A, plus AR plus AR squared plus AR to the third plus AR to the fourth plus, and it goes on and on, blah, 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 plus AR to the n minus 2 plus AR to the n minus 1 plus blah, blah, blah. So what if we had A times S? Oh, no, I'm sorry, R times S. R times S. R times S. Well, then we would have, let's make a better R. Okay, we would have we multiply every term of that series by R. So AR plus AR squared plus AR to the third plus AR to the fourth plus AR to the fifth plus so on, blah, 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 AR to the n minus 1, because we're adding an R here. Remember, if we multiply by R, we must add an R there. So this term becomes n minus 1. And this next one becomes A R to the n, because R to the n minus 1 plus 1 is R to the n only. Now, what if we had S minus RS? So, what we have now, when we have S minus RS, you can see that many of these terms cancel out. And I should have put dot, dot, dot there. And these all will cancel out except for two terms. We have that cancels there, that cancels there, that cancels there. So we have A, and this is minus A r to the n. So now we have a formula. We factor out S, and we got 1 minus r equals A 1 minus r to the n. And so S is equal to A to the 1 minus r to the n on 1 minus r. So now we have a formula that tells us the sum for any number of terms of this original sequence or series, that if we wanted to take the let's say the sixth term, and what is the sum of the sixth term? So we got 1, 2, 3, 4, 5, 6. That's 6 terms. So that would be now if we were given the condition that A equals 1 and R equals 2, we want to add up 6 n equals 6 terms. So we have 1 plus 2 plus, and A is always 1, so that's 2 squared, that's 4, plus 8, plus this is whatchamacallit, 16. All right. Yeah, I'm just a little distracted now because I had a problem with this before, so please forgive my distraction. 2 to the 4th is 16, and this is 32. Okay, so we got 32, 16, 8, 4, 2, and 1. So this is 10, 20, 23, and that's 6. So that should be 63. Okay, so now we have our formula. If we had n equals 100, let's say 60 or 600, it would be very difficult for us to calculate. This formula gives us that answer. So our original question was, what are the 6 terms given A is 1 and R is 2? So we have S equals 1 times 1 minus 2 to the 6 over 1 minus 2. And 2 to the 6 is equal to 2 to the 3rd times 2 to the 3rd. And that's equal to 8 times 8. That's 64. Okay, 1 minus 64 over 1 minus 2, and that's equal to 63. So S equals 63, and we have exactly the same number. But now we have a formula that is easy to use for the series if we wanted to add the series up to any number of terms. And as you can see, this series also is a divergent series. The numbers just keep getting bigger and bigger. And also, they would tend to oscillate between, I think, let's try n equals 2. N equals 2, so 1 times 1 minus 2 to the and 1 minus 2 is equal to that's equal to 1 minus 4 over 1 minus 2 equals, that's minus 3 minus 1 equals 3, which is correct. So I guess they will always be positive on this. But anyway, that's a nice way to you can do this similarly with like a Fibonacci series, and you can get what they call the Binet formula for the Fibonacci series, which gives you a similar formula for calculating any Fibonacci number in terms of multiples of the golden number raised to any power of n. So there are very useful methods that can be utilized in series. Let's see, there was one last series that I wanted to take a look at, and I'm trying to think about it right now as to what it would be. Oh, yes. Okay. This is a Taylor series, okay? A Taylor series. If you have the sine function, you can say that that's equal to a0 plus a1 x squared plus a2, or let's not call that theta, let's call that argument x. X to the third plus a3x to the fourth plus a5x to the fifth, and that goes on indefinitely. And it turns out that if you take derivatives, and we haven't done that yet, we haven't taken derivatives yet, but the derivative of the sine function is the cosine of x, and then that is the negative sine of x. So if you take the derivative of the cosine of x, and then that's the negative cosine of x, and then that is the positive sine of x. What am I doing? I'm trying to rush. Sine of x, and that's cosine of x, and so on. And these would be equal to, this is 2a1x. Whoops, I forgot. I made these. This is 1, 2, 3, 4, and so on. So this is a1, and this is 2a2x, 3a3x squared, 4a4x to the third, 5a5x to the fourth, and actually, no, I'm trying to rush this too quickly. This is a1 plus 2a2x plus 3a3x squared plus 4a5x3 plus blah, blah, blah. This is 2a2 plus 2 times 3a3x plus 4 times 3a5x squared plus blah, blah, blah. This is 3 times 2a3 plus 4 times 3 times 2a4x plus 5, 4, 3x squared, a5, and so on. And then what you do is you solve for these 4, 5 times 4 times 3 times 2, A5. You set x equals 0, and so that top one is 0 equals A0, 1 equals A1, 0 equals 2A2, -1 equals 3 times 2A3. And now you've got a series. You've figured out the coefficients, and then you have a sine of x equals 1 minus 1 over 3 factorial x cubed plus 1 over 5 factorial x5 minus 1, 7 factorial x to the 7, blah, blah, forever. And now you have a series, an infinite series. They call it a Taylor series, a polynomial series that yields a trigonometric function. That's the power of calculus. We'll be looking at that later. But this is a very important series that we'll look at. There's a similar one for the cosine. For any function whose derivative yields a periodic, let's say in a periodic way, for example, e to the x, its derivative, let's say y equals e to the x, well, dy dx is equal to e to the x. And then d squared y dx squared is equal to e to the x. You've got that function can be represented by a Taylor series. The cosine function of x, if y equals, so dy dx equals minus sine of x, and d squared y dx squared equals minus cosine of x, and then d cubed y dx the third equals sine x, and you can just keep going forever, cosine of x. And that can be represented by a Taylor series. So Taylor series and series in general serve a very useful function in mathematics in helping us to understand solving problems. It's a neat way to solve problems that you can't let's say, more directly. In fact, there's no way when you look at a Bell distribution, what they call a Gaussian curve, e to the minus x squared over some number, something like that. E to the I would have to take a look. I'm just going by the seat of my pants here, but x, y. This is a bell curve. You all know a bell curve from school when they take grades and they look at the 95th percentiles and so on. And you got standard deviation. That's 66%. And then this is 95% is two standard deviations, I believe. Anyway, you cannot integrate this function directly. There's no way that you can integrate this function. So to get the, let's say, the area under the curve. So you have to use an infinite series, a Taylor series. A Taylor series to get a function. And you can integrate then that Taylor series and then that's how you get the answer. So you can find the answer indirectly by having gone to a series as opposed to trying to find the solution directly. And because there is no direct solution. So series really do provide a very important role in mathematics. So sequences and series, they're kind of related to one another. Um, and they form a branch of mathematics that is fascinating. In fact, for the Fibonacci sequence, there's an academic society called the Fibonacci Association, and they publish since 1963 a quarterly called the Fibonacci Quarterly, and in that mathematicians provide all kinds of interesting discoveries about the Fibonacci numbers, all of the properties and characteristics of Fibonacci numbers and the golden number. And they've been printing this ever since 1963. Much of it is really high level stuff that it would look like looking at hieroglyphics because of the nomenclature that they use, the mathematical nomenclature and the symbols that they use. Um, is kind of like learning a language in its own right, but you would have difficulty trying to understand what's in there. But I had four problems that I created, original problems, and had them published for people to solve. They have what they call advanced problems and elementary problem section, and I had a couple printed in the elementary problem section. Anyway, I hope this has been of interest and utility to you. I hope you have a better idea or at least feel for series and sequences. There may be more that I will pick up on that I might have overlooked, unfortunately, in this. Maybe in figuring out, let's say, how to represent a series using mathematical nomenclature, because you're going to see these things with the summations and how do you get those? How do you get those? How do you get those awful looking, very complex looking symbols? And how do you go about doing it? And some of it is just basically fiddling around until you get the mathematical behavior you want to get. So we can take a look at that in the next video, as well as limits, because I think the limits are a little bit more relevant because when we get to derivatives, and you could see that we're on the verge now of talking about calculus, limits are critical, absolutely critical to understanding derivative and understanding an integration, an integral. So anyway, we're almost there, and this is Mathman, hoping you all stay well. And if you are stuck indoors, it might not be a bad idea to try and hone up on your mathematics skills. So I wish you all well, and until next time, this is Mathman saying so long.